j equal to 0 to 9 e to the s of j squared. So, right, minus e to the si over j equal to 0 to 9 e to the s of j and times e to the s of I over j equal to 0 to 9 e of s of j.
First one is not square. The first one is not
Oh,
square.
this one cancelled, so this should not be square. Yep. Right? What is this over here?
S
S of I. So S of I minus
of I squared.
S of I squared. So this will be S of I 1 minus S of I. So the derivative of this with respect to S of j, when I is same as j, happens to be this part over here. Okay, so same way, if we went through it for the case I not equal to j, what you will find is the answer will come out to be, all the details are in the handout to save time. So this will come out to be minus si minus sj. And I'll show you the handout in a second so that you can see. So now what we can go is, we can start plugging all the values over here. We'll be able to compute it. So let me show you the handout for the rest of the detail. If you can flip one of the lights over here. Okay, so anyway, I've already put the handout over here, so let me quickly log in. Okay, so if you go to the lectures for 2020, one of the new handouts you will see is softmax derivative and derivation of delta. So this is the same picture I drew indicating, right, there are multiple paths to get to this over here. So anyway, just like we discussed, there are two cases, I equal to j. And again, if you do this, this is what we just did on the board, si 1 minus si. And very similarly, if you follow the handout for the case I is not equal to j, you can easily verify this. This will come out to be minus si minus sj, right? Okay, so our goal, remember, is, if we can find the delta over here, this delta over here, right? And this delta over here, delta 1, and so on. which is essentially partial L over partial S0 plus partial S0 over partial lowercase s0. Similarly, partial L over partial S1 plus partial S1 over partial S0. So all of those, 10 components need to be added because there are 10 paths leading to each one of these deltas inside the neuron. Okay, so anyway, so computing delta, so this is the delta I inside a softmax function, and just like I mentioned, the loss function is typically used as a cross entropy with the softmax, which is basically y of j. So y is the expected output, log of sj. So this is the output of the n summation over all the outputs. This is called the cross entropy loss, right? So for example, if I wanted to do, let's say, partial L over partial S1 as an example, what will this be? Can you tell me from here? So I'm taking the derivative with respect to capital S1, right? Derivative of the log is 1 over S1. And because I'm doing it for S1, what does that mean? J is 1.
Y1.
So it will be Y1 over S1, right? So anyway, again, why do I care about this? Take a look over here, the picture. So first I have to do partial L over partial S1, right? Then further going into all the 10 paths over here to accumulate the gradient over here. So the partial L over partial S1, what I was saying, is pretty easy. Or partial L over partial S0. It's pretty easy. Okay, so here I give an example of what if we were to do just delta 1 of the neurons, right? So just like we discussed, there are 10 paths going into the neuron. So once again, just very briefly, if we were interested in this delta 1 over here, right? Then one path is up to here. One path is up to here. Another, similarly 2, 3, and similarly over here is the other path. So you can see partial L over partial S0 plus partial S0 over partial S1. So this will be partial L over partial S0 times partial S0 over partial S1, right? From here to here. Okay, then partial L over partial S1 times partial S1 over partial S1, right? Plus, keep going, partial S, partial L over S9, right? And then partial S9 over S1. Okay. So for example, what will this part be, as an example? For the cross entropy, remember? Y9 over minus Y9 over S9. Perfect. Would be this part, correct? Now, what will this be? Okay, remember we discussed two cases. I equal to J
minus S1, S9.
was Si 1 minus Si. And I not equal to J was minus Si Sj. So my question is, if you were to compute this, which case is this? I equal to J or I not equal to J? So wouldn't that be
Minus S9.
minus S1 S9? It doesn't matter which one you put first, right?
That's a multiplication.
Okay, so everybody got it? So all the parts can be easily computed? Okay, so anyway, going back over here. So these are the, just for delta 1, partial S0 over S1, S1 over S1, S2 over S1, S9 over S1, right? So again, in this case, all of these cases are, like take a look over here, S0 over S1. So I is not equal to J, so what will be the derivative? Minus S1, S0, right? However, in this case, take a look over here. S1 over lowercase s1. So isn't that same, I equal to J?
Yep.
So the derivative will be S1 times 1 minus S1, right? Anyway, if we go through it, manipulate the sum over here, the beautiful part is it will come out to be very, very simple. So all those partials and everything come out to be simply minus y1 plus s1 for delta 1. So in general for delta I, can you guess what will this be?
Minus yi plus
Minus yi plus si. Or we can say delta equal to s minus y in terms of vector form.
Yep.
Okay, isn't that pretty neat? Even though the softmax turned out to be a lot of exponentials, but if we use, once again, the cross entropy as the loss function, then this will come out to be this part, right? Do we have to use cross entropy? In some data sets, maybe simple least square error will be the better loss function, right? So this is, once again, with cross entropy as the loss. Okay, so what if somebody says, what if mean square error is the loss? And we are using still softmax and last layer. So what will be the delta in the last layer in the neuron? Okay, no big deal. We know all the paths we can accumulate, we can go. So let me show you what if we don't use cross entropy. So if you go down over here to the next page. Okay, so computing delta I for a softmax neuron with mean squared error as the loss function, right? So again, I put half 0.5 yi minus si squared. So again, the expression for the delta in terms of the partials do not change. Okay, what will change basically? This part will become y minus a, right?
Yeah.
Okay, y minus a. As you can see, 2.5 will cancel. Okay, but this one we already know. If I equal to j or I not equal to j, we already know how to do that. So the question is, will they reduce to a neat form that you guys saw in case of cross entropy and the softmax? So in this case, again, if we plug in all and try to see if we can reduce it. Okay, the final answer is slightly more complicated. Okay, so it turns out it is minus y plus s. Okay, this one is element by element multiplication. So for example, if I gave you two vectors, 1, 2, 3. So let's say this is some vector A, some vector B, let's say 4, 5, 6. Okay, so then A, this circle with a dot in it, B, basically means the answer will be 1 times 4, 2 times 5, 3 times 6 will be the answer. Okay? So it's an element by element multiplication. So in our case, the delta as a vector in the last layer neuron, so all of this delta as a vector is minus y. And what is y? The expected output. Okay. So for example, let's take a look at the MNIST example. If we fed in a picture of digit 2, can you tell me what would be the y vector?
0, 0, 1,
0, 0, 1, so 0, 1, 2, and 1, 2, 3, 4, 5, 6, 7, 8. Right? So this will be the y. So do we know why? And what is capital S?
the actual.
The actual output from the softmax, and how will that be computed? Remember, E over S, J over J equal to 0 to 9, E of SJ, right? SI. Okay, so anyway, we can easily, as we were doing the forward pass, after we produce the sum, we can do those exponential calculations. Again, element by element with S, then Y transpose S, and so on, S transpose S. So this is how, if we use mean square error as the loss function, right? Okay, so in your assignment 5, I'll have you play with this, where you will actually program this. So from programming point of view, as you can see, we don't care how we came to the result, but this is what you will be putting in your Python code, right? And very similarly, if somebody said your loss function over here is cross entropy, then if you wanted to do back propagation, how will you compute the deltas? According to this expression, right? Okay, so now let me give you an idea of the next topic.
How many types of loss functions?
How many kinds of loss functions? I'll say in the hundreds. Okay. So in fact, anytime you do new research in this field, you pick a new problem, often you try to come up with a loss function which will do the best job on that kind of data. So I'll say a vast majority of being good in the deep learning field is trying to learn how do you come up with a loss function. So there are some standard ones that we discussed, but let me see if I can show you very briefly.
People started categorizing those, like if you want to do like image recognition, these kind of loss function.
Yes. Yeah. So depending on the type of field, yes, it varies a little bit. So let me see if I can. As soon as this comes back, maybe I have to wait a few more minutes. So while I'm waiting, okay. So anyway, to summarize, the key thing that I would like you to remember from our current discussion is if you have a binary classification problem, meaning true, false, somebody having, diabetes, no diabetes, cancer, no cancer, right? For any time the decision is true, false, 0, 1 type of decision, what is the loss function that we typically use?
Sigma? Yes. Sigma.
No, sigmoid is the activation function. Mean square error. Okay. Anytime we have multi-class classification. So here loss function will be cross entropy. In general, not always, in general, okay? And then there will be very specialized loss functions as we go and take a look at different problems, and you'll see what they are, right? In this particular type of problem, what is the activation function we'll use in the last layer? So here it could be sigmoid or tan hyperbolic or real. Those are the popular ones. Again, some data sets work better on sigmoid, some data sets work better on tan hyperbolic, some data sets work better on real. Okay? For a multi-class classification, what is the activation function you will use in the last layer? Always softmax. So remember, you will never use softmax in the beginning or in the hidden layer. Always, only in the last layer you'll use softmax. And again, it makes sense because the purpose of it is to distinguish the output that is producing a high value from the outputs that are supposed to be not recognized, right? So we want to create a high distinction, and that's why we take the exponential to amplify that effect further, right? Okay, so moving onwards, anytime somebody gives you a 6-class, 8-class problem, suppose you wanted to do flower identification, what kind of flower it is, you have 30 species of flowers, then obviously you use softmax in the last layer, right? Okay. So now, another important aspect of deep learning is as our networks become more and more involved, meaning not from number of neurons point of view, but also if we have a lot of layers of neurons, okay, the training becomes difficult. Okay, so there are two goals to the training. First goal obviously is we want to come up with as good of a solution as possible so that not only on the training data set we get high accuracy, so we want high accuracy on training as well as unknown or test data set. Okay, so during our development, obviously somebody gives us a test data set, but once we have verified on the test data set in real life, we'll be given some unknown data, and our job is to be able to do as good of a job on the unknown data as we did on the training data, right? Of course, preventing overfitting is key over here. Okay, so another problem that we run into, especially with deeper networks, is faster training. Because the training time can easily be hours or days or weeks or months. Okay, so if we are not careful, so what I'm trying to say is over here, remember, let's take a very simple example. We had two sets of weight matrices over here, W1, W2. So in the beginning, they will be randomly initialized. We'll do a forward pass, then we'll go backwards, adjust the weights according to the gradient descent algorithm. And if you recall, gradient descent algorithm will do the following, right? Some learning rate partial L over partial W1, right? Same thing W2 minus partial L over partial W2. Same thing for B1 and B2. Partial B1 and B2 equal to B2 minus alpha partial L over partial B2, right? Okay, together this W1, W2, B1, B2, in the technical terminology, we refer this as the model of our network. So this is the model of network. Meaning once it's trained, we'll be fixing W1, W2, B1, and B2. And again, in the technical terminology, collectively, we refer to this as theta. So theta is our model. Okay. So alternatively, rather than writing these individually like this, okay, in the mathematical terminology, we could write this as theta equal to theta minus alpha partial L over partial W1 or W2. See, the inverted triangle basically means the derivative or the gradient. Okay, now we are taking derivative with respect to W1 or W2 or B1 or B2. So once we put theta over here, all that means is, you know, if this is W1, this is the derivative with respect to theta, right? And derivative of what? Derivative of the loss function. Okay, so you could say L of theta. So this is the general gradient descent description in mathematical form. Okay. Now some people use L as in denoting the loss function. Some people use J as the loss function. Okay. Some people use E for error as an example, right? They all mean exactly the same thing, so loss is same as a J. I could write the, you know, Y minus A squared as J rather than L, right? So it doesn't, so don't be confused whether somebody's using J or L. It's really the same thing, right? Okay, so when we come to deeper networks, but anyway, if I was using J, then this will become theta minus alpha delta of theta, J of theta, meaning J is a function of theta. Is it really a function of theta? As you can see, the output of the network, which is used in computing the loss function, depends on the weights and the biases, right? So that's why that makes sense. Okay. So the question over here is, and one of you actually had asked me, was this is what we call the learning rate. Okay, so what should be the learning rate? Okay. Should it be 0.8? Should it be 0.5? Should it be 0.01? Should it be 0.001? You know, what is a good value? Of course, it depends on the problem. Okay. So here's the interesting part. If we pick, let's say, a high learning rate, then as I briefly mentioned to you last time, okay, let's say I plot, here's our loss function, okay, and let's say here's the set of weights, or I could put a theta over here because theta is many, not just one thing. And we can only visualize two-dimensional data. We cannot visualize, you know, higher dimensions or three, but cannot have more than three, right? So let's pretend it's a very simple network. with a single W. Okay, then if we take a look at the loss function, easy case will be, it's like a convex function. So even if we start at W randomly, our loss is high, but using gradient descent, which is essentially doing partial L over partial W, and keep adjusting the weight, it will keep moving, and hopefully will settle in the lowest one. Whatever that W has the lowest loss, so that's our target in our training, right? Okay, so the question is, what happens if I pick high learning rate or very low learning rate? Okay, so let's pick the scenario. If it is high learning rate, you can see it will be adjusting the theta with a bigger value, right? So it will be, high learning rate will go something like this. It may go here, then 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 may go here, and finally settle. Meaning it will oscillate perhaps something like this until it comes to the final point, right? So on the other hand, what if we pick very, very small learning rate? Then what will happen? So it will basically be moving very slowly. It will not oscillate, but it will. So the execution time of our code will be very high, right? Ideally, what do we want?
Higher
So ideal case would be we want a learning rate high enough so that it is able to get to our goal, but not that high so that it starts to oscillate at the end. Okay. So a lot of, especially the last 2 years, a lot of research, or maybe last 3-4 years, I would say, a lot of research has gone into what is the optimal value of the learning rate. Okay. There have been hundreds of papers written on trying to identify for a given problem. So nobody knows the optimal answer. We have come close, but still there's room for improvement. So what are the possibilities? Because as you start playing with more advanced networks, you'll be picking some, this is called learning rate schedules. So these are basically algorithms that gradually reduce it, start high, so that as we come closer to our target, right? So anyway, the convex is a very simple case. Mathematically, we can prove it based on the convexity. What is the optimal alpha, how it should be reduced. But here's the thing, our deep networks do not behave, the loss function does not behave in a convex manner. In deep networks, okay, so first of all, there are many local minimas. Okay? You can easily get stuck in one of these local minimas, whereas the best answer is over here. Right? If you picked a very high learning rate, even though you